Hello everybody and welcome to another episode of the Physics Corner, wherein we take simple physics problems, set them up, and show you how to solve them. I'm your host, Dr. Christopher Sorolla. In today's episode, we're going to take a look at something called the Mr. Ed problem. Let's begin. So, Mr. Ed is a famous talking horse from an old TV show, so we're going to go ahead and freely borrow that idea. And he has an owner named Wilbur, and they get, of course, into wacky situations because that's what sitcoms do. We're worried about a specific situation today that involves physics. So imagine the following happens. Wilbur, the owner again, decides that he needs to go sell some vegetables at the local market and hitches Mr. Ed to a cart full of vegetables and says, "Mr. Ed, let's pull this cart to market so we can sell all these wonderful vegetables." But Mr. Ed says, "Well, Wilbur, I'm sorry, I can't do that." And Wilbur asks, "Well, Mr. Ed, why not?" And Mr. Ed says, "Well, Wilbur, I'm an intelligent horse, as you know, and I've been reading up on physics. And specifically, there is a law of physics, the third law of motion, which states if you exert a force on an object, it will exert an equal and opposite force upon you. So if you hitch me to the cart, I try to pull the cart will exert an equal and opposite force on me. Those two forces will cancel each other out. If there's no net force, there's no motion. Therefore, I can't pull the cart. Therefore, there's no point in hitching me to the cart. I'm not going anywhere." So, well, I think we can all agree that horses can, in fact, pull carts places, or that motion of any kind can happen. Because if Mr. Ed was correct, if you think about it for a moment, nothing could ever move anywhere. So obviously, Mr. Ed's made a mistake in his logic, but what is it? And how can we use physics to convince Mr. Ed otherwise? So again, remember, we're pitching this to Mr. Ed. He's an intelligent horse, right? So another reason to tackle this particular problem, besides the general physics nature of it, is that it allows us to talk about a specific kind of technique called free body diagrams. And we're going to use free body diagrams to argue for the fact that Mr. Ed can, in fact, pull the cart if he just tries hard enough. So let's get started. All right. So, don't worry about the artistic value of my work here. We are talking about physics, not art. But hopefully the picture does show the general idea of what we're talking about. Mr. Ed and the cart. Now, to make things a little bit simple, we have both the cart and Mr. Ed on a horizontal surface. The harness that hooks up Mr. Ed to the cart is also perfectly horizontal for our purposes here. And that means that anything that is pulled along that harness will be perfectly horizontal. Okay, so what a free body diagram does is it simply takes a look at an object and sketches out the directions of the forces acting upon that object. Then you can take those pictures that you drew and use those to derive or create equations of motion. You can combine those with other information you might have on hand to therefore solve for whatever you're trying to solve for. In this particular case, the question we're asking is, okay, can Mr. Ed in fact pull the cart hard enough to get the cart to move? So that's our question. All right. So free body diagrams are therefore these simple pictures. Notice how I've stated it. A free body diagram does not invoke acceleration or velocity or displacement or anything else. It's simply forces, and only forces that we're talking about here. So let's do this in turn. Let's take a look at Mr. Ed, and let's take a look at the cart. So what I can do is I can sketch a picture of, or a free body diagram of Mr. Ed. Now, notice I don't need to redraw the horse or anything like that. I just need to draw a circle, or sphere if you prefer, to represent Mr. Ed. Because at least at this stage of our knowledge, that's all that we need. We don't need any fancy pictures. We just need to have some central object about which we can sketch forces. On top of that, when we sketch our forces, we're just going to draw them as arrows because forces are vectors, right? So we can do that too. So what kinds of forces are acting on Mr. Ed? Okay. Well, Mr. Ed has a mass, and because he has a mass, he therefore has weight. Weight always pulls straight down. So we can represent the weight on Mr. Ed as the mass of Mr. Ed multiplied by gravity, little g, like that. Okay. Now, the ground holds Mr. Ed up. He's not sinking into the ground or falling through the earth, right? So there is a normal force acting on Mr. Ed. Now, Normal force, to remind everybody, is a force that is perpendicular to the surface. The surface is horizontal. The normal force pushes away, so the force is pushing Mr. Ed upward. All right, so let's go ahead and put a normal force going up like this. And because I want to distinguish Mr. Ed from the cart, I'm going to keep using subscripts as labels where appropriate. All right, what else is acting on Mr. Ed? Those are vertical forces, but Mr. Ed is trying to pull the cart. Well, Mr. Ed is here. He's trying to pull the cart this way. So Mr. Ed is exerting a force on the cart. Now, for our purposes, we're going to assume that the gear is perfectly horizontal. We understand that in reality that might not be exactly true, but let's pretend, at least for the purposes of our problem, that it is. And a force exerted along a line is called tension. So there's a tension being exerted by Mr. Ed on the cart. Now, before we get into that too much, though, we have to ask ourselves, is this the force that Mr. Ed is exerting on the cart, or do we want to draw the cart's force on Mr. Ed? This is tricky, and this is part of Mr. Ed's quandary. So let's think about this before we get to drawing this arrow any more further. It's the forces on Mr. Ed that I'm asking about right now. So if Mr. Ed exerts a force on the cart will, by the third law, exert a force on Mr. Ed. And if Mr. Ed tries to pull the cart forward, the cart will try to pull Mr. Ed backward. So before we get too far along, let's draw the tension there. Notice how I've done that. Now, I'll come back and draw this arrow in a little bit. But there's a tension acting on Mr. Ed that we're talking about. Now, by the way, there's no subscript on this because, and again, the third law does state this, the forces are equal in magnitude and opposite direction. So there's no need for a subscript. Okay. With that in mind, is there a force going forward acting on Mr. Ed? This one's a little trickier to see, but Mr. Ed, of course, has feet or hooves, and those hooves are connected to the ground right here, right? And what Mr. Ed does is he pushes backwards on the ground, if you will. The ground is going to push Mr. Ed forward. So there's a force from the ground, and I'll just write that out to make that kind of obvious that that's what I'm talking about, acting on Mr. Ed's feet, and of course, therefore, the rest of Mr. Ed. This is, in fact, how you and I walk in everyday life. Most of our force that we experience from the ground, of course, is normal force to hold us up. But if you want to propel yourself forward, if you think about this carefully, you actually push backwards on the ground. The ground, therefore, in response, pushes you forward. So the ground is doing two things at once. It's holding you up, but it's also pushing you forward if you're trying to walk forward. So, strange enough, the ground is what's pushing you forward. You're not pushing yourself forward. The ground is doing that. Why is the ground doing that? Because you're pushing the ground backward. In any case, these are the forces acting on Mr. Ed. And that's it. There's no springs in this particular picture, so we don't have that to worry about. And so I can write down a series of equations expressing all this. Now, here's the order in which we go next. Once you draw a free body diagram and you have your arrows for your forces pointed in the correct directions, usually the picture will suggest an approach to take for setting up coordinates. And remember, forces are vectors, right? If they're vectors, we need to identify directions. So let's do that. So let's go ahead and in this particular case say the positive x direction will go to the right and the positive y direction will go up. Notice also that x and y are at right angles to each other, as they always are for two-dimensional problems. Okay. And this way, I can set up force equations in x and in y. Okay. This brings in the second law of motion. So Newton's second law says that the sum of forces equals mass multiplied by acceleration. All right, so let's draw that out. So the net force in the x direction, which I can write like this, okay? By the way, there's a variety of ways to write this down. This is consistent with some of the textbooks we use here at Southern Miss, but if your textbook uses a slightly different version, for example, if it says something like this, uses a summation sign, that's all fine too. It means the same thing. So in any case, the net force in the x direction acting on Mr. Ed. Now, a lot of times the textbooks will use an equal sign here, and that's perfectly true, but I'm going to make it a little bit of an equals arrow, if you will, because this is a set of directions, if you will, telling me how to do this. This is not where I'm going to end up. This is telling me how to get my equation. Let me explain. So, in the x direction, I have the force from the ground. That's pushing forward, so ground force like that, okay? If you look here, tension is going backwards in the x direction, so I subtract that, and that is my sum of forces. So this becomes this statement here. Now, we can't stop at this point. We have to keep going. What else is there to do? The law of motion, Newton's second law, states that sum of forces equals mass times acceleration. The whole point, we hope, is that Mr. Ed is able to accelerate the cart. So, and let's think about this. The cart is originally at rest. Mr. Ed is going to start moving the cart forward, so therefore there must be at least some initial acceleration, right? And so we'll set that equal to the mass of Mr. Ed multiplied by the acceleration, like that. So, and that's the whole point, right? We're trying to show that this is possible, so let's write that way. Okay. Now, we also need the y direction as well, so let's write an equation for that. Same sort of logic. The forces acting in the y direction. Again, a lot of times it's set as an equal sign, but the equation that I really want is this stuff. So I'm just using this to indicate how I'm going to get there. All right. Well, in this case, there's a normal force going upwards acting on Mr. Ed. And there's the weight of Mr. Ed pulling downwards like this. Right? Now, hopefully, as with all normal surfaces, there will not be a Mr. Ed or cart accelerating into the ground or flying up above the ground. He's going to stay horizontal. If there's no vertical. So if there's no vertical motion, make sure I say this correctly, there's no vertical motion, the net force in vertical for Mr. Ed is 0. Okay. One more equation to write. These are equations of motion, or more force equations more carefully, that express the forces acting in x and y. But there's one more equation we need in this particular case, and that will be a friction equation. So friction is equal to a coefficient of friction multiplied by normal force. Right. Now, why am I bringing it up? Well, turns out that for Mr. Ed, the reason that he can push his hooves on the ground and the ground pushes him forward is because of friction. Think about it this way. If he was on a perfectly slick surface, like say a very icy rink perhaps, then he would be slipping and sliding and he wouldn't get any purchase, if you will, on the ice. There would be no force of friction to help drive him forward. So this force here that I identified as force from the ground is really a frictional force, if you think about it. And if we do a friction force problem, we always need to incorporate this individual formula relating friction to coefficient and normal force. So that's why it's there. All right. So those are the equations acting on Mr. Ed. Now, here's the problem, or at least the thing to say about all this. That's not really helping us a great deal yet. Why not? At least for this particular problem. And the reason is because the whole thing that Wilbur wants to happen is to get the cart to market. I mean, Wilbur could hitch the cart to his truck or pull it himself, or a variety of different ways of getting a cart to move. He's just asking Mr. Ed to do it. But the whole point is to get the cart to move, isn't it? So what we're really interested in are the forces acting on the cart. So this is a good way. By the way, there's nothing incorrect about these equations. These are perfectly legit equations. The picture is just fine. But what we're really interested in is the cart, so let's do this free body diagram approach for the cart. Let's try that. So, same idea. I'll label it cart to identify it that way. Let's go ahead and drop some equations of motion for the cart. Now, this will be a little bit quicker since we've done this already, so let me go through this a little bit faster. The cart has a weight. We'll call it C for cart if you don't mind, and G like that. We'll go normal force acting in cart going up like this, so we have those together. Now, what about the horizontal forces acting in the cart? Well, again, the whole point is Mr. Ed is trying to pull the cart to the right or forward in our picture, so again, that's tension, and tension on the cart will be acting like that, right? Also, again, there's no subscript on tension because this is an equal and opposite pair of forces, right? What about the cart itself? Are there any other forces acting in the cart? Well, the cart is standing still, and as we know, if the cart is a physical object in contact with another physical object, another solid object, there is a force of friction, Before it moves, we call that static friction specifically, but there is a force of friction. Even when it's rolling, there will be some friction. But to get it started, we need to overcome the initial static friction. So there'll be a static friction force acting on the cart like this. And I'll just say little f for friction for the moment like that. Okay. All right. Same approach then for our directions. And I think the same kinds of ideas will work just fine for us there. So positive y going up and positive x to the right. Okay. So here's our free body diagram for the cart. Let's take a look at these. So we also again have our friction equation. So I'll just write that down in general. So friction equals this. In this case, it's acting on the cart. Let's see here. What else do we have? Let's do the force in y first, because it's going to look very similar to what we just did for Mr. Ed. There's a normal force going up for the cart. There's the weight of the cart going down. And again, that will be 0. Okay. Here's the interesting one. How about the forces acting in the x direction on the cart? Let's write that one down. So the net force acting on the cart in the x direction, from our picture, and again, this is one of the reasons to draw a free body diagram so you can see it in front of you. Tension's going to the right. So, tension like that. Friction, trying to hold it back, to the left, this way. And then, if we get it to accelerate, it'll be the mass of the cart, because that's the object in question, multiplied by acceleration. Okay. And here's our answer then. Can we convince Mr. Ed to pull the cart? We know horses can pull carts, so it's possible, at least in theory. How would he need to do that? What's the physics explanation? First things first, the worry that Mr. Ed had was that if Mr. Ed, pulls the cart, then the cart will pull back on me, Mr. Ed, and therefore those forces will cancel and nothing will happen. But notice our free body diagrams, plural, tell you how that is wrong, tell you why that's a mistake. Because even though this tension equals this tension, that's true, notice they're being applied to different objects. This tension applies to Mr. Ed, this tension applies to the cart. They don't apply to the same object. So equal and opposite forces, that's a true statement. There's nothing wrong with this statement as Mr. Ed has read it. It's in his application. Equal and opposite forces are applied to different objects. If they apply to the same object, then he'd have something to talk about, but that's not what's happening. They apply to separate objects. Second thing then, and this is a consequence of this, when you apply the equations of forces and motions and such things, apply them to one object at a time. That's especially relevant here for applying Newton's second law of motion. One object at a time. I want to find out what the cart is doing, right? In this sense, I couldn't care what Mr. Ed is doing. Okay? It doesn't matter what Mr. Ed is doing. What I care about is what the cart is doing, or more carefully, what is being done to the cart, if you will, right? And in this case, it's the cart tension and force of friction that I need to worry about. So here is our then answer to the question. Let me block it off and simply say this. If the tension is the same as the force of friction that Mr. Ed exerts on it, this would be 0, and there'd be no motion. Because this is a static friction, and let me put a little s in here to represent that, because it's a static friction, if Mr. Ed doesn't exert enough tension, then a static friction will be the same as the tension, and again, they'll cancel, and there'll be nothing there. Let me go back up over here and make a modification to show you what do I mean by that. Static friction isn't equal to a coefficient times the normal force. Static friction is really an inequality or equal to coefficient times the normal force, which is to say the amount of static friction that an object feels depends upon what you exert on it in part. If I have an object that I barely touch, it's barely going to exert any static friction. If I pull or push really hard, it will pull or push back with a large amount of static friction until we get to a certain point, which is our next step. But the amount of static friction changes. So only if I exert, or in this case, Mr. Ed exerts enough tension, will we have a change. So here's the condition. The cart will move if the tension is greater than the static friction. And this is what we can say to Mr. Ed. Look, Mr. Ed, quit being so lazy. You need to pull harder. That's simply all you need to do, Mr. Ed. You haven't tried hard enough. If you pull hard enough, you will overcome the static friction. You will get the cart to accelerate. And by the way, once the cart accelerates, it'll be easier to keep moving. And there's a couple of reasons for that, which we're not dealing with in this particular problem here, but I think everybody knows it's easier to keep an object moving, especially if it's on wheels like a cart, than it is to get it started in the first place. So that is the answer to our question. So notice we didn't have to introduce any numbers. We didn't have to do any fancy calculations for this. You can do that if you wish, but today we wanted to show what this is all about by just simply making arguments. And again, one of our major, say, reasons for doing all this is to show off the power of the free body diagrams. So free body diagrams don't require any artistic expertise, as you can see. I just need to be able to draw a circle and arrows and label them appropriately. It's the physics knowledge that you have to apply, of course, to draw the arrows in the correct directions and with the correct labels. But once you have that down, the free body diagram does a great job of suggesting coordinates that are very common or very good to use for your situation. And it helps you derive equations, force equations, like all these equations here. And that's the Mr. Ed problem. All right, everybody. This video series has technical support from Sidney Cautraw and Sophia Turner. Funding is supplied by the University of Mississippi and the University of Southern Mississippi. This video was shot in Hattiesburg, Mississippi itself. I am your host, Dr. Christopher Cirola. Thank you very much for your attention, everybody, and clear skies.